our next invitation, our next guest. So, professor Rui Almeida vai apresentar nosso próximo convidado, que é o professor Hermenegildo Borges de Oliveira, da Universidade de Algarve. Rui Almeida, é com você.
Boa tarde a todos. É com muito prazer que eu vou apresentar o professor Hermenegildo Borges de Oliveira, que é da Universidade do Algarve e ao mesmo tempo investigador no COMAF, um amigo à longa data, e que nos hoje vai falar sobre alguns resultados sobre o P. Laplacian. Vou passar a palavra para ele.
Speak in English, but if you in any time you can ask me in Portuguese. I understand I can translate or something if you have some difficulty. Although it's not my mother language, I think you can speak in English. So, first of all, I would like to say that good afternoon to everyone there in Brazil, in South America, and good night to everyone here in Portugal, and good day to everyone that might be in a different time zone, perhaps. Good night for them. First of all, I would like to invitation that the people organizing these seminars to invite me to give this seminar. The title of my talk of this seminar is Some Results on PDU Laplacian Problem. This talk is based in the joint work with Michel Chipot from Zurich. Okay. Can you see my second slide? Yes? Everything is okay?
Sim.
Okay. I will consider a very, very simple problem, but that gives us a lot of open questions in mathematics, at least from the point of view of mathematical analysis. The problem is to consider the P. Laplacian problem, or in this equation here, where we append this with Dirichlet zero boundary conditions. But what is most important is that the function of nonlinearity P depends on the solution itself. So this P is varying with the solution itself and with the space dimension as well. I will start first with the local problem. So in this case we have this problem that I told you. F, the right hand side, is a given data, and P is a function from R into 1 to plus infinity, is our exponent function of nonlinearity. At this time, we should remark that this P of U can be seen as a composition function of that we call Q, and in turn depends on the space time in the space variable. So some knowledge on Lebesgue and Sobolev spaces with the variable exponents is required to study this, but not so much, as we will see later on. Okay, some remarks and applications of this problem. Okay, this problem is the natural extension of P of X Laplacian, a problem that was introduced by Zhikov, as Professor Patricia Pucci said before, in 1986, when he was studying the Lavrentiev phenomenon. Later then, during the 90s and during the first decade of this century, a lot of people start to work these problems, mainly motivated by the applications in electrorheological fluids, where you can see the nice book of Dinning, Ariuletto, Esto, and Ruchika, and in problems of image segmentation and image restoration, and you can see some of these applications in the book of Cruz Uribe and Alberto Fiorenza. These problems with the P of U Laplacian appear in some applications in computer vision. In some of these models that people study in computer vision, they minimize functionals where here this model of gradient of u depends on P and on the solution itself. And there is experimental work and numerical work by Tiroler with a lot of plots and a lot of numerical examples that, considering an exponent that depends on the solution itself, produce much better images in computer vision than when you consider P depending on X or P just a constant. So we are motivated for the P of X Laplacian problems, but also there are some applications. Some remarks in this P of U Laplacian problem. After our paper is from 2019, and when we were submitting, it was sent to us a paper by Andreanov, Bendaman, and O'Hara, where they study a very similar problem, where besides our equation, in our equation, they had some u here. We don't know why they used this u here, perhaps because of the technique to prove the existence of solution. So, but from mathematical point of view, what is the main difficult in these kinds of problems? The main difficult is because this P is varying with the solution itself. You cannot study these problems in duality terms in fixed Banach spaces. So these spaces, they are moving with the spaces where we are looking for the solution are moving with the solution itself. So you cannot fix them in this Banach space. And even you don't, these spaces, they are in fact Banach space because they neither are vectorial spaces or sometimes don't have other properties. One other big issue in these problems, that was the main problem when the Andreanov, Bendaman, and O'Hara tackled this problem, is when you have approximate solutions u of n, let us say, with exponents p of n, these solutions might belong to distinct Sobolev spaces, and so you cannot pass to the limit so easily. What was the idea of Andreanov, Bendaman, and O'Hara? So once they could not use the Minty trick or this abstract Minty argument, because V is a monotonous operator, so you can use this machinery if P is constant, they used a tool that pulls everything down to the L1 space, and then they use the description of this of weakly L1 convergent sequences in terms of Young measures. So they use a very strong machinery to prove the existence. As we will see, we will handle with this situation here in a different way. So just to remind some of you that are not used with the Sobolev and Lebesgue spaces with variable exponents, let us say for simplicity that our domain is bounded, has a Lipschitz continuous boundary, and let us consider a measurable function q from omega in our domain, and is greater or equal than 1. So we define this LQ space as all the u measurable functions that has this modular finite. This is a modular and is finite. We can prove that this space equipped with this norm that is called the Luxembourg norm becomes a Banach space. So this LQ space is separable for any q greater or equal than 1, and it is reflexive if in addition it is less than is greater than 1 and less than infinity. So in particular, we have the space of infinitely differentiable functions with the support compact in omega is dense in the space LQ. And we have, of course, this notation that we should call when we use q subscribed minus. This is the infimum of our q of x, and q subscribed with plus. This is the supremum of our q of x. So we can, from the definitions of this norm and this modular, we can take a lot of relations, but the best one that will relate, because as you can see, this is not equal to this norm to the power q of x. So we have some relations that at the end of the day will be okay for us to take the right estimates. So we have these relations between the norm and the modular of our Q. So we can define the order conjugate pointwisely, and we have also generalized order inequality, in this case for U belonging to Q and V belonging to the dual of LQ. As far as to the Sobolev spaces with variable exponents, we define these spaces in this way: U belonging to LQ with all the derivatives, first derivatives, and such that the gradient of U belongs to this Lebesgue space with variable exponent. In this case, we assume that at the boundary of the trace of these functions is 0 on the boundary of omega. So this kind of Sobolev space, they inherit many of the properties of the Lebesgue space with the variable exponent, in particular the separability and the reflexivity. So we have these embeddings, LQ in LR, W1Q and W in W1R, whenever Q is greater than R, almost everywhere in omega, of course. One of the main drawbacks of these spaces is that unlike the classical Sobolev spaces, when we say classical Sobolev spaces, we mean Sobolev spaces with a constant exponents. Smooth functions are not necessarily dense in this space, W10Q. So in fact, this closure of this infinite differentiable functions with support compact in this norm is strictly contained in this space. So this is a larger space. But there are some conditions on this exponent Q so that these two spaces are equal. So sufficient conditions for that. What are these functions? These functions, they are continuous over the entire omega, the closure of omega, and satisfy this older relation. Where here we have a function omega, that is the modulus of continuity that satisfies this logarithmic condition. So therefore, these functions, they are usually called log-order continuous functions. So if Q is log-order continuous function, so this space, this space here is dense in this space there. And so it is okay for our approximations, and we can work very well. We have, in that case, the Sobolev inequality of Q star here is generalized the Sobolev conjugate, and it is important to see that here, I cannot see here because we have the norm of U in L infinity is less or equal than this for Q, the infimum of Q of X greater than the space dimension. So let us go back to our problem. So we define the set where we are looking for the solutions to our problem as this. Note that this is just a notation. This is not a Banach spaces. This is not even a vectorial space. This is just a space where I say that U is in W1, 0, and as this modular is where this modular is finite. So the solutions we have in mind to look for, they are defined in this way. So our P of U is bounded between two constants that are strictly contained in the interval between 1 and infinity. So we may assume that F is in the Sobolev conjugate of our W1 alpha 0 space, where alpha is the minimum or the infimum of our P of U. We say that U is a weak solution to our problem if U is in that space, U as the first derivatives, trace with the 0 trace, and the modular is finite. and moreover satisfy this equation whenever v is for all v is in the same space. And here, looked at here, is the duality pairing between Sobolev spaces with the constant exponents. Okay. So let me see. Just a remark on the classical theory of monotone operators. So if our gamma of our p of u were constant, then we could use the monotonicity of the operator A of it. We then could use this coercivity condition and this Gauss condition here, and the theory of monotone operators will assure us the existence of a solution U to our problem. And moreover, that solution would be unique if our monotonicity condition would be strict. Note that here the constants, the exponents here, they are the same, and moreover, this gamma prime is the older conjugate of our gamma. So everything is okay because I'm dealing with the space W1 gamma 0 and with its dual space W minus 1 gamma prime. However, if our operator is our gradient of u to the power p of u minus 2, gradient of u, with that condition, our p of u bounded, when we have, we have the same monotonous property, and we have the coercivity now is satisfied for our c to the power alpha, where alpha is the minimum of our p of u, and our Gauss condition is satisfied through the dual of beta, and beta is the maximum of our p of u. So we have a gap here. So in one way we have a condition with our alpha, in the other way we have a condition of beta. And we could not apply the theory of monotone operators if alpha is less than beta. So this is one of the main problems and drawbacks that I guess that Andreanov, Bendaman, and O'Hara found when they tried to study this problem with the usually technique of the Minty argument. So more or less by the same time that that paper from Andreanov, Bendaman, and O'Hara appeared, it was only at that time, 1 year later, that was published by Zhikov, a work where that we can use to solve this problem with the Minty argument. And it is particularly important when we have the coercivity estimate is apart from the Gauss condition in that sense. So what is the idea? This is an idea that goes back to Zhikov, that many other authors probably in the past have used it, is to regularize our problem with a divergence of the same operator, but here the power is beta, is the maximum of our p of u. So if we consider that our f is in w minus 1 beta prime, and you know that if it is in w minus 1 alpha prime, it is of course in w minus 1 beta prime. So we have the notion of a weak solution. Now we are working in the classical Sobolev spaces, and where here we can say that the duality is in the classical Sobolev spaces. So what the idea of the proof, we will find the conditions such that for each epsilon positive there exists a solution to this problem. So what you have here, we can if we define our monotonous operator in this way, of course that if we're given an arbitrary w in L2, we have from the boundedness of our p of u that it satisfies also this condition. Moreover, as I said, if our f is assumed in this space, it is also in that space. Okay, We have, for this operator, we can prove that it is strictly monotonous, so we can assure uniqueness at the end. We have the coercivity condition with beta, and we have the growth condition with beta prime. So we can assure the existence of a unique solution whenever is given an arbitrary W. We find a unique solution to our problem, our regularized problem. So, moreover, we can take an estimate for this solution, taking V equal to U here. We find that the gradient of U in beta is bounded where the constant is independent of W. It depends on epsilon, but it is independent. So we go here and we use this compact embedding. So this U in L2 norm is bounded because of that boundedness of gradient of U in beta, L beta. So we can apply the Schauder fixed point theorem. We define mapping that to each W in this space, where this constant C is that constant C there, gives us that maps to each W maps the unique solution to our approximated problem. So the proof of the continuity of this operator is very usual. We consider that a sequence of Wn converging strongly to W in L2. So we have, moreover, from the estimates in this estimate here, 1.17, that this gradient of U of n in beta, they are also bounded. So by means of reflexivity, we can extract subsequence that we still label by n, converging weakly in W1 beta 0 and strongly in L2. So taking U of n and Wn in the places of U and W, we arrive at this equality here. So then we take here, we replace here V by U of n minus U. We have this inequality here. So because Wn converges strongly here, so we have a subsequence at least that converges almost everywhere. So we can use the Lebesgue theorem to prove that this operator here converges to this one here strongly in L beta prime. What we have just to assume here is that this term here converges to this term there almost everywhere. So to have that, we have to assume that P is a continuous function. So this is one of the assumptions that we have. So we can use the Minty trick with, as usual, replacing V with U minus and plus some positive delta and zeta for zeta in this space, and we end up in this equality whenever for all z in this Sobolev space. So we have that in fact our U is the U of W from the solution that we either part, and from the uniqueness of the limit we have this strong convergence in L2. So what we have proved that for each epsilon positive there exists a solution in this space to our approximated problem here. Note again that P of U of epsilon is bounded in between alpha and beta. So we will pass now this problem to the limit, letting epsilon goes to 0. So we have to obtain some estimates. This one here is easy to obtain, where it is important that the constant does not depend on the epsilon. So using the generalized order inequality, we can prove that the gradient of u of epsilon in the power alpha is bounded by a constant C2 that is also independent of epsilon. So we again can extract subsequences converging weakly in W1 alpha 0, and by means of compactness, we have that u of epsilon converges strongly to u in L2 and almost everywhere to u in omega. From the continuity, P of this term converges from P of u of that term. So we can use one of these equations, let me see. We can use this 1.27. It's not 1.27, is this equation 1.26, and with epsilon in the place with this, and together with 1.31. Let me see. No, this is not correct. It's better. So it's not better to go. Whoops. So in the final part, we use this lemma to prove that this gradient of u to the power p of u is bounded. So this is the part where the work of Chekhov comes in our work. This is lower semi-continuity when we have some sequence of exponents q of n bounded between alpha and beta, converging almost everywhere in omega, with the gradient of un converging weakly in at least in L1. So we have the convergence in alpha, and we have this boundedness here for some constant that does not depend on n. Then by this result of Chekhov, the gradient of u belongs to LQ, and we have this lower semi-continuity property. And once that we have proven before, is bounded, we have that gradient of our u, where q here is meant by p of u. Okay, so this proves that passage limit. We have, although the proof of this lower semi-continuity Chekhov requires much more hypothesis, and it's much more deeper. For our purpose, we are using this this small part of the Chekhov lemma, and for this we have proven in the very elementary way that lemma it's not so difficult to obtain. So I will skip this technical part. What we have now, using the data identity, we can and replacing u of epsilon with u of epsilon n minus v, we have this inequality for all v in this space, and this is the most important part that comes now. Similar as we did in some of that inequalities before, we will, in the limit, we will have this inequality for all v in this space which is infinitely differentiable with the compact support in omega. What is the problem? The problem is that I would like to have this for all v in our set of our, where we are looking for the solutions. So for this, what we need that this space here is dense in our space there. But to have this, we have to as I said before, when I talk about the subleved spaces with the variable exponent, the exponent, in this case p of u, needs to be order continuous. So what we have, we start this is the main restriction for our existence result. When alpha is greater than the space dimension, we have this order space with this second exponent 1 minus d over alpha, contains our W1 alpha 0, where our U is, because U is in that space that is contained in this space. So we are saying that U is order continuous. So we have to impose some condition on P so that P of U is order condition. In that conditions is that we need that P is Lipschitz continuous. A continuity is not enough to have P of U order continuous. In that case, so all starts with this restriction here, and we have this space dense in that space. So we can take in this inequality using the Minty trick U minus and plus some delta zeta with zeta in a proper space that we have, and we have the identity that we need to prove our result. So this is the existence results. What we have proven is that to prove some parts of our existence result, okay, we are working in some W1 of P of U space that is moving with the solution itself, but due to that recursivity condition that depends on alpha and to the growth condition that depends on beta prime, we work in two Sobolev spaces with the constant exponents, mainly in the greater Sobolev space, in the greater or smaller with or can say with the greater exponent, W1 beta. So that is the idea. So this is the restrictions we had to make to prove our existence result. So our P of U is bounded between two constants that are strictly between 1 and infinity. Our F is in W1 minus 1 beta prime, and here is W minus 1 alpha prime. So this space is contained in that, so we just have to assume this condition here. By compactness of W1 beta in L2, we need this condition here. And at that time, we just needed that P was a continuous function. In the second claim, we have more or less the same assumption, with extra assumptions that alpha needs to be greater than D. So the maximum between these two elements is D, so alpha needs to be greater than D. And moreover, our P, that our function of nonlinearity, P of U, is Lipschitz continuous. So we have the existence of weak solutions. So when you are talking about uniqueness, is a much more difficult problem, because when you are talking about uniqueness, what you do, you consider two weak solutions, let us say U1 and U2, and then you test this after you made some algebraic calculations, you test your equations with the difference of these two solutions. But you don't have no guarantee that the difference of two functions is in the same function space. U1 is in this function space, U2 is in this function space, and where is U1 minus U2? You don't know. So I don't know either. So this is a main drawback to prove the existence or the uniqueness of solutions. So Andreanov and Bendaman and O'Hara solved the uniqueness with a lot of extra conditions. For instance, assume that the boundary is of order continuous of some alpha that is not the same our alpha, of course. Moreover, F is essentially bounded function, and moreover, uniqueness is just for weak solutions that are Lipschitz continuous. So this is a main restriction in the problem. But we cannot prove in a general dimension, but when you cannot prove in a very complex situation, you try to simplify the problem. So we tried and we solved the problem, the uniqueness for the 1D problem. 1D problem is more or less easy to talk, just have to assume here that F here is strictly positive to have some monotony condition so that we can prove the uniqueness. So I don't know how much time do I have? Hello?
Está perguntando quanto tempo tem?
15 minutos. 15 minutos.
15 minutes? Okay, it's
Yes.
enough. It's enough. So what we did here to prove the of unique, it's very important because this is send us to real analysis in one dimension, and this is some of us understand very well the problems in many dimensions, and when we come to one dimension we can say, oh, this is so difficult, but not. It's we should try sometime to solve the same problems in one dimension and to see what is the mathematics that we need. So the main idea is just to use that the f is positive, to say that this operator here is decreasing, and then to prove that u prime cannot be a constant. And due to the boundary conditions, you can say that u vanishes in some point c. And it's just in one point, because if there is another point, then this would contradict this decreasing, this monotony of this operator here. So we split the problem into two problems in that c where where the derivative of u is 0. So, and then we prove for each one of these problems the existence of a unique solution by showing that these right-hand sides, they are uniformly Lipschitz continuous with respect to u. This is. Then we prove that the function u of g, that is solution to this problem, in the solution, the function u of h, that solution of this problem, are increasing. U of g is increasing and u of h is decreasing when c runs in the whole interval from -1 to 1. And then we show that this unique solution to that problem, when they c run in the whole interval, they only merge, or they are only equal in the point c, and this our uniqueness is proved. So let us speak a little bit about some open questions in this local problem. So despite many efforts of many important people working in these problems, it seems that the only works in this direction to prove existence and some uniqueness are these two works by Andreanov, Benjamin O'Hare, and by this mine work jointly with Michel Chipot. The restriction alpha greater than d of the space dimension is very strong, because from the physical point of view leaves out interesting situations, as the case when p of u is in the interval between 1 and 2 for dimension d equal to 2, or in the interval between 1 and 3 for d equal to 3. So it's a very serious problem to come down for alpha smaller than d. So it seems that different machinery has to be applied. The uniqueness, even for alpha greater than d, but d is greater or equal than 2, seems also to be a serious problem. We have some ideas, some work on progress, but some partial results, not very good results. So we don't know if we will publish or submit to publish that result or not. Another important problem is the parabolic version of our problem that is still open. So, as I said, the problem is very simple, but many interesting situations are open. So, I have to say that when you work with Michel Chipot, you need to say something about the non-local problem, because he has a lot of works in non-local problems. So along with that local problem, we studied in the same paper the non-local problem. What is the non-local problem we are talking here? Here, our exponent p depends on a functional b of u, where b of u can be one of these norms, the gradient of u in the norm alpha, where alpha is the minimum of our piece, or else can be the LQ norm, but in this case the Q has to be not larger than the Sobolev conjugate of alpha. So our P is again a function from R and is greater with values greater than 1, and our B is a functional from the Sobolev space. What we have for the weak solution in the solutions we are trying to prove the existence is in this sense, where here we have not to be confused with the local problem, because here our P of B of U is a real number, is a constant, is not a variable exponent. Okay, because our B of U is the norm of the gradient of U, or is the norm of U. That is a constant, does not vary. Okay, the idea of to prove this theorem is a little bit tricky. We consider a sequence of problems that approximate our P Laplacian problem, that we can call it for each real number. We define the unique solution to this problem that we know that exists, because this is a monotonous operator of P of lambda is constant, so it satisfies all that conditions of the that the monotonicity, the coercivity, and the growth condition with the same exponents. We assume again that our alpha, our P of lambda is greater than alpha, is less or equal than beta, and our F is in the same place. Okay, we obtain some estimates for the gradient of lambda that do not depend on lambda. We can infer that our B of U of lambda, let me call that B of U, is that function there, is bounded as long as we assume that this B function is bounded. Okay. Then we consider this mapping from this segment into itself, and we prove using the same ideas, starting with the sequence converging to lambda by the continuity of P. We have this convergence here, and we will apply this lemma here that says basically when we have this convergence, F is in this space for Q less than P, that P there, and UN is converging strongly in this W01Q, so we have this identity there. That's what we do. Oops. Sorry, where was the lemma? The lemma was here. So we have this U of lambda n converging to U of lambda by means of that lambda. And we have this convergence as long as B is also continuous. So we have that B needs to be bounded and needs to be continuous. Finally, we have a fixed point, and U lambda 0 is then a solution to this problem 2.4. The most difficult part is to prove this result, mainly to prove this convergence. First we prove the weak convergence, then we prove the strong convergence, but this is more or less technical. I will skip some of the details. And what we have in this existence result is these conditions here. We have our function P exponent of nonlinearity in this non-local problem is bounded, and alpha is greater than 1 and p is less or equal than beta. We have f in this dual space of W1 0 alpha. B is bounded and continuous. So there exists at least one weak solution to the problem 2.1 in the sense of definition that we defined before. So the most difficult part is to prove that strong convergence, therefore, before in this lemma here, to prove this strong convergence here. But this is some technical details. If someone wants to see it, please send me an email or some message. Then, or the paper is online, can be seen. And if you have any doubt, please contact me. What I would like to call your attention is that for the non-uniqueness of this non-local problem, this we can say that this problem is not well posed in that sense of Adamar, that it has to be, Adamar said that a problem is well posed when it has at least a solution. The solution is unique and depends continuously on the data of the problem. So, but this problem, the solution is not unique. Let us see why. Let us take two real numbers in this interval, distinct real numbers, and consider u1 and u2 two solutions that are corresponding to these two distinct exponents. So we have two problems. So we may choose a function b, that non-local function b, so that b of u1 is different from b of u2, but we may well consider function p as in as before, such that this p of b of u1 is equal to p1 and p of b is equal to p2. So we are saying that u1 and u2 are both solutions to the problem. So we don't have uniqueness in this problem. In some remark that we wrote in the final part of our paper, there we had a lot of open questions, more than solved problems. We wrote that it would be interesting in some cases, non-local case, for instance, that it's, as I told you, it's much more easier to relax our assumptions on the right-hand side f, allowing just to be an integrable function, to be L1 function, for instance. This question was already solved by some guys that I will talk a little bit later. And we have also extending our results to the parabolic case. This question is half solved, and this question, also this third question about the asymptotic behavior of the solution, is also half solved, let us say. So, as I told you, for the local problem, the only results that, for the best of my knowledge, that we know are that work by Andreonov, Bendaman, and O'Hara, and our result with Chipot and Oliveira. But for the non-local problem, a lot of people start to work on these problems. For instance, a very familiar and strong research group, these two Russian guys that are friends of mine, Stanislav Antonchev and Sergei Shmarev. But it was first by Xiaoling Zhang, two Russian guys, two Chinese guys, that they solved the first question that we wrote in that remark. First, in a paper from the paper spent a lot of time in the referee, I think, because the paper I was aware of the preprint perhaps 2 years before it was published. It was only published, as I can say here, in the final part in 2021. But in the final part, in the end of the 2019, I was already aware of the work of these two Chinese guys. They relaxed the assumption on F to assume that F is just in L1, but here they proved the existence just for the known local problem, but in the framework of entropy solutions. They also solved the parabolic non-local problem that me and Chipo, we didn't touch in the parabolic problem. We were spending more time with the uniqueness, because we know that the parabolic non-local problem it was not a problem. The parabolic local problem seems to be more or less a problem. Let us wait. And the idea of the proof, it was to use some time discretization and combine it with the technique that me and Chipo developed in our work. In the works of Antontsev and Shmarov, Stanislav Antontsev and Sergei Shmarov, they considered also the non-local problem, the parabolic version, with specific non-local functions, where b of u is here not the gradient of u, but u to the power q, where q is in this narrow interval between 1 and 2. And the p of b of u is less than 2 is greater than 2d over. This everyone knows this is needed because of compactness. We have some compactness of some subleft space in L2, so we need this. Go below this is very difficult. And in fact, for d equal to 2, this is 1, but for d equal to 3 is larger than 1. So in this situation, assuming these extra conditions that the boundary of the bounded domain is of class C2, and the function p, the exponent of nonlinear function p, is differentiable. So they prove the existence of a unique strong solution that is global or local in time. Moreover, they show that every strong solution vanishes in finite time. It is well known that in these p Laplacian problems in the parabolic, when p is between 1 and 2, you have this finite speed of propagation property that we can call the finite extinction in time. Moreover, in another paper, they consider the right-hand side with f depending not only on the space variable, but on the solution itself and on the non-local function as well. So with these extra conditions, this means more or less some gross condition on this right-hand side, the authors prove the existence of a global in time strong solution. But again, in these conditions. So this is the state of the art to my best knowledge. So a lot of work must be done in this problem, and I hope that some of you one day can join us to work in these problems. So thank you very much for your attention. If you have some questions, please go ahead. In Portuguese, if you want.
Thank you very much. It's a good presentation. Some question, please. Some comment.
Parece que eu vi alguém ao fundo, mas não sei se era questão ou não.
Sim. Max, sim.
Bom, acho que vou fazer a pergunta em
Em português, sim, sim, por favor.
A Patrícia não está aqui. Então, basicamente, a minha pergunta é o seguinte: você não ganha nada se você pedir uma regularidade extra do teu expoente? Né? Ou seja, sei lá, se você tivesse a rua analítica, por exemplo. Eu sei que eu estou indo na direção contrária do que normalmente as pessoas estão, mas uma regularidade...
Uma regularidade na função P, não
na função P, exatamente.
Na função P. Sim, tal como mencionei neste artigo de Stanislav Antonsev e Sergei Shimarov, quando eles consideram P em C1, portanto, eles conseguem provar aqui para o problema não local, não para o problema local. Conseguem provar alguns resultados um pouco melhores. Mas para o problema local, que é aquele que está mais em aberto, não parece que vá adiantar alguma coisa. Portanto, a não ser que considere alguma condição nesse expoente P, de modo, porque o que precisa é que esse expoente... Agora vou continuar a falar em português. Foi o Max Souza que estava a perguntar-se qualquer coisa sobre a regularidade do P, penso eu. Sim, Max?
E foi isso mesmo, foi isso mesmo. Eu acho que você praticamente respondeu, né? Basicamente.
Pois, vamos para o problema mais complicado. O que nós precisamos aqui neste P, ou P de U, é algo como vai depender da solução e, por sua vez, depende da variável do espaço. Quer dizer que este expoente que está aqui, esta composição de P com U, tem que ser log order continua. Tem que ter aquela condição de continuidade com o módulo de continuidade logarítmica. E isso só acontece se nós considerarmos o nosso alfa maior do que o ínfimo dos P's de U seja maior do que a dimensão do espaço em que estamos a trabalhar. E isso é o grande problema, porque se nós, portanto, aumentando aqui a regularidade disto, quer dizer que ainda, portanto, não precisamos ter muita regularidade, até fomos à regularidade mínima, que é a log order continua. Portanto, nós só precisamos de que o espaço W1 0 alfa esteja contido num espaço de order, e para que é o C0 1 menos alfa sobre D, em que, neste caso, o alfa terá que ser maior do que D. Portanto, evitar essa condição da continuidade com módulo, aquela continuidade de order com módulo de continuidade logarítmica, é o principal problema que nós temos aqui em atacar a situação. E daí torna-nos muito difícil virmos para valores de P menores do que a dimensão do espaço.
Ok, tá bom. Obrigado mesmo, Hermenegildo, pela resposta.
Nada.
Mais alguma questão? Comentário? Bem, se não há mais comentários, quero agradecer mais uma vez a bela apresentação que nos fez e passava a palavra para a Sandra nos falar das próximas sessões.
Ok, obrigada, Rui, obrigada, Hermenegildo, excelente palestra, e por todos, e também agradeço aí